Stop scrolling. Give me a few minutes. Not a boring history lesson. This is the story of the most important accident in human history. An accident so ordinary, so easy to miss that it happened right next to a campfire, and nobody at the time had any idea what they were looking. For 2 million years, 2 million, the smartest tool on Earth was a sharpened rock, and it broke every single time. One hard hit, and you started from zero again and again, generation after generation, century after century, with no way out. Then, near an ordinary fire, someone reached into cold ashes and pulled out something that shouldn't exist. A rock that bent instead of breaking. That one accident built Egypt, built Mesopotamia, built empires that still show up in history textbooks thousands of years later. And then, eventually, that same accident collapsed one of those empires completely, because the ingredients it depended on came from a supply chain so fragile that one broken link could starve an entire civilization of weapons overnight. And buried underneath the whole story is a twist most people have never heard. One civilization cracked a metal so advanced that it defeated Michael Faraday himself, one of the greatest scientific minds who ever lived. That same civilization built a pillar that has stood in the open air for 1600 years, through monsoons, through heat, through modern pollution, and has never rusted. Not once. We're going from a shepherd's fire to a bronze-dependent empire collapsing under its own weight, to Faraday's failed experiment, to a pillar that, by every normal rule of chemistry, shouldn't still be standing. Let's go. 7,000 years ago, a sharpened rock was your entire world. A stone edge for hunting, a stone edge for defense, a stone edge for cutting hide, for scraping bone, for building anything resembling a life. And every single time it met something harder than itself, it shattered in your hand. Picture that moment. You've spent hours chipping this edge into shape, patiently, carefully, striking flake after flake off a core with practiced precision passed down from your parents and their parents before them. And then one hard strike against bone, one unlucky angle against another stone, and it's gone. Ruined completely. There's no fixing it. There's no repairing it. You just start over. From nothing. Every single time. For almost the entire span of human existence, that was daily life. Not a bad week, not a rough patch. The permanent condition of being human for roughly 2 million years across every continent our ancestors ever reached. Entire generations were born, hunted, raised children, and died without ever holding a tool that could survive more than a handful of hard uses. Skill mattered enormously in that. The difference between a well-made flake and a clumsy one could mean the difference between eating that week and going hungry. But even the finest stone tool in the world still had the exact same fatal weakness baked into it from the start. Archaeologists who have tried to replicate this process by hand, using nothing but period-accurate techniques, describe it as genuinely difficult work. Striking a stone core at precisely the right angle with precisely the right force to remove a clean flake instead of shattering the whole piece into useless fragments takes real practice. Entire childhoods were likely spent learning it. And after all that training, all that inherited skill passed down around a fire from an older relative to a younger one, the finished tool still had an expiration date measured in uses, not years. Would you have accepted that forever? Most people would have had to, because there was nothing else on offer. But somewhere, at some point, someone didn't accept it. Someone looked at a broken edge and thought, there has to be something better. They needed a material that could bend instead of shatter, something that could hold an edge instead of losing it after one good hit. So, according to the patchy evidence we have, people experimented. They threw stones into fire. They dunked them in water. They tried heating and cooling and combining in every way their imagination allowed, and none of it worked because stone simply doesn't change its nature. It only breaks. And then, one day, near an ordinary fire, something extraordinary happened by complete accident. Maybe it was a shepherd, tending a flock and building a fire ring out of whatever rocks were lying nearby. Maybe it was a potter, constructing a kiln to fire clay, unknowingly surrounding the flames with the wrong kind of stone. Either way, the fire had been ringed with strange, greenish, streaked rocks. Nothing like the plain gray stone everyone was used to working with. When the flames finally died down and the ashes cooled, someone reached in expecting nothing but soot and cinders. Instead, they found something that shouldn't have existed. A reddish, heavy, oddly warm lump, sitting exactly where a rock used to be. It wasn't a rock anymore. What was it? They struck it with a stone hammer, almost certainly out of habit, expecting it to shatter the way everything always had. It didn't shatter. It dented. It changed shape without breaking apart at all. Try to imagine watching that with absolutely zero concept of chemistry, zero idea that metal even existed as a category of thing. What would you call an object that bends instead of breaking? Ancient people, in cultures separated by oceans and thousands of years, kept reaching for the exact same word: magic. That magic had a real name, and the science behind it is genuinely elegant, even though nobody standing at that fire understood a single syllable of. Burning wood in a half-enclosed space produces carbon monoxide, a gas that aggressively strips oxygen away from anything nearby. Copper ore holds its copper atoms locked tightly to oxygen atoms inside a stable mineral compound. Break that chemical bond with enough heat, and liquid copper pools free at the bottom of the fire, cooling into a solid, malleable lump once the flames die down. This wasn't a one-time fluke either. Archaeologist Ronald Tylecote spent decades of his career rebuilding ancient furnaces from scratch, using only period-accurate materials and techniques purely to test what temperatures they could realistically reach. His findings were striking. Ordinary pottery kilns from that era could already hit the exact heat copper needed to melt without any modification at all. Nobody had to invent brand new technology to stumble onto this discovery. The discovery was hiding inside technology people already had, sitting there patiently waiting for someone to notice. So, copper spread fast, by ancient standards, across Iran, across Anatolia, into Mesopotamia. People stopped waiting around for lucky accidents and started deliberately hunting for those strange green-streaked stones. Soon you might have owned a copper needle, maybe a small copper blade or a decorative bead. It felt like the future had arrived. But copper carried a weakness nobody could ignore for very long. It was soft. A copper knife dulled quickly, bent under real pressure, and honestly lost to a decent, well-made stone edge in a straight fight. People needed something harder, something that kept copper's flexibility, its resistance to shattering, but added real strength underneath it. And that's exactly what happened. Roughly 5,500 years ago, almost certainly through relentless trial and error rather than any single flash of genius, someone, somewhere, discovered that mixing copper with a small amount of tin, roughly 9 parts copper to 1 part tin, produced something entirely new, harder, stronger, capable of holding an edge that copper alone could never manage. Bronze didn't just improve the toolkit available to ancient people, it rebuilt entire civilizations on top of it. Egypt rose on bronze weapons and bronze tools. Mesopotamia rose the same way, temple by temple, army by army. Entire empires ran on one specific ratio of 2 metal, discovered by people who had never heard the word chemistry, working purely off fire, persistence, and the occasional happy accident passed down as sacred knowledge. Bronze changed more than warfare. It changed farming, with stronger plowshares turning heavier soil. It changed art, with bronze casting allowing far more intricate statues and ceremonial objects than stone ever could. It changed status itself. Owning bronze became a visible marker of wealth and power, something a farmer with a stone hoe could see across a field and immediately understand. Kings commissioned bronze doors for their palace. Temples commissioned bronze statues for their god. An entire economy, an entire social hierarchy reorganized itself around access to 2 specific metals and the skill required to combine them correctly. And the skill was not trivial. Get the ratio wrong, work the alloy at the wrong temperature, cool it too quickly or too slowly, and the resulting bronze could be brittle or soft or riddled with weaknesses invisible until the exact moment a blade snapped in battle. Master bronze smiths became some of the most valuable specialists in the ancient world, their knowledge guarded and passed down through careful apprenticeship, generation after generation. But bronze carried a hidden flaw, and it wasn't inside the metal itself. It was in where the ingredients came from. Copper was common enough, deposits scattered across a wide swath of the ancient world. Tin was not. Tin deposits sat concentrated in a small handful of far-flung locations, some deep in the mountains of what's now Afghanistan, some clear across the sea in Cornwall, on the far southwestern edge of England. Getting tin to a bronze-working city meant caravans crossing deserts, ships crossing open water, supply lines stretched thin across thousands of miles of unpredictable terrain, and even more unpredictable politics. Entire ancient port cities existed for one purpose alone: moving tin from wherever it was mined to wherever it was needed. Think about what that actually means. Every bronze sword, every bronze plow, every bronze temple ornament in the ancient Near East depended, at some point in its supply chain, on a resource that had to travel further than most people in that era ever traveled in their entire lives. What happens to a civilization when a single fragile supply chain like that finally snaps? You're about to find out, because that's precisely what happened. Around the 12th century before the Common Era, a wave of disruption, invasions, famines, and the collapse of long-distance trade routes across the eastern Mediterranean broke the tin trade that bronze-dependent kingdoms had relied on for centuries. Palaces that had stood for generations went dark within a matter of decades. Historians still argue argue over exactly why, but the fragility of that supply chain sits at the center of almost every explanation. Underneath every bronze-dependent empire, the entire time, sat something everyone had been walking past without a second glance. Iron, not rare, not imported from across an ocean, not fought over by caravans and navies, just there, in nearly every hillside, every riverbank, every patch of reddish soil on the planet. So why did it take thousands of extra years for anyone to actually use it? Because iron simply refuses to melt at bronze temperatures. Copper melts at just over 1,000 degrees Celsius. Bronze melts even lower. Iron needs upward of 1,500 degrees Celsius, and a basic ancient wood fire barely scraped past 700 or 800, no matter how skillfully it was built. That gap wasn't a small obstacle to work around. It was an outright wall. The wall finally came down through two accidental improvements that had nothing to do with iron. First, charcoal, which burns significantly hotter and cleaner than raw wood ever could, and the bellows, a simple leather bag, worked by hand or foot that could pump forced air directly into a fire's base, feeding it oxygen and pushing furnace temperatures past 1,500 degrees for the very first time in recorded human history. Once that ceiling broke, iron had nowhere left to hide. Around 3,200 years ago, in what's now central Turkey, the Hittite civilization mastered this exact process, and they guarded it like a state secret worth more than their own border. Iron sold for more than the price of gold in Hittite territory. Only kings, only generals, only the innermost circles of political power were permitted to carry it. Diplomatic letters between Hittite rulers and neighboring kings survive to this day, showing rulers politely, and sometimes not so politely, requesting iron as a gift, only to be turned down or given token amounts. Do you think a secret that valuable can stay buried forever? It couldn't. When the Hittite Empire eventually collapsed, somewhere around 1,200 years before the Common Era, caught up in the same wave of disruption that broke the bronze trade routes, that knowledge scattered across the ancient world almost overnight. Smiths who once worked under royal supervision suddenly had no royal supervision left. The Iron Age began nearly everywhere at once. Not through gradual invention, but through the sudden collapse of the system that had been hoarding the secret. Suddenly a common farmer could own an iron-tipped plow. A common soldier could carry an iron spear without needing inherited wealth or royal favor behind him. The material that had once belonged only to kings now belonged to everyone. Now here's where this story stops following the path you were probably taught in school. Because while Egypt and Mesopotamia usually get the credit for the Iron Age in most textbooks, another civilization was working iron completely independently and doing it earlier than almost anyone realized. In villages like Malhar and Dadapur in northern India, archaeologists have recovered iron tools and slag dating back roughly 3,800 years, centuries before the Hittites ever touched the metal at all. This wasn't a borrowed technique that slowly drifted in from the Middle East along some ancient trade route, arriving generations after the fact. The evidence, the layered dating, the local ore composition, the absence of any clear trade link, points somewhere else entirely. India appears to have discovered iron completely on its own, independent of anything happening further west. And India didn't stop there. It pushed the material further than almost anywhere else on Earth at the time. Around 2,500 years ago, Indian metalworkers developed a technique now known as crucible steel. They sealed fragments of iron, charcoal, and specific plant matter inside a small sealed clay container, then cooked it for days at extreme, sustained heat, allowing carbon to slowly and evenly bond into the iron's internal structure. What came out the other side was called wootz steel, and it was extraordinary, sharper than almost anything Europe was producing at the time, tougher, capable of holding an edge strong enough to cut clean through a lesser blade on contact, according to accounts that circulated across the ancient and medieval world. That steel traveled by trade route all the way into Damascus, Syria, where local smiths reforged the ingots into the weapons that eventually made the region legendary across 3 continents. Damascus swords were said to slice a silk scarf floating gently in mid-air. They were said to shatter weaker European blades in a single clash. Whether every story was exactly true or slightly exaggerated by centuries of retelling, one thing is not in dispute. For centuries afterward, nobody outside India understood how any of it was actually made. Nobody, including one of history's most famous scientific minds. In 1819, Michael Faraday, yes, that Faraday, the same man who would later help unlock the mysteries of electromagnetism itself and change the modern world, personally studied samples of Indian wootz steel, trying to reverse engineer its secret using the best chemical analysis available at the time. He failed completely. Isn't it strange to imagine one of history's greatest scientific minds standing defeated in front of a technique developed by anonymous blacksmiths more than 2 2,000 years earlier, the real answer wouldn't surface for another century, and it took modern materials science with electron microscopes and metallurgical imaging Faraday could never have dreamed of to finally find it. Researcher Sharada Srinivasan, who has spent years studying South Asian archaeometallurgy, helped establish that Indian smiths were consistently achieving carbon concentrations far higher than European methods could reliably reach, and that this process formed microscopic carbide structures inside the steel, tiny, evenly distributed particles that gave the metal almost supernatural strength and flexibility at the same time. Indian craftsmen were essentially performing nanotechnology centuries before the word existed, guided purely by inherited skill, patience, and generations of careful, repeated observation. But wootz steel isn't even India's strangest metallurgical achievement, not by far. Standing in Delhi right now, today, in this exact moment while you're watching this, is a solid iron pillar, 7 meters tall, roughly 6 tons of dense, worked metal, forged approximately 1600 years ago during the Gupta period, one of classical India's great scientific and artistic golden ages. It has stood outdoors, fully exposed to the elements, through 16 centuries of monsoon rain, blistering summer heat, freezing winter nights, and now, on top of everything else, modern industrial pollution. And it has never rusted, not once. How does 6 tons of exposed raw iron survive over 1,000 years without a trace of meaningful corrosion when a modern iron fence post left outside can rust through in a matter of decades? For a very long time, nobody had a real, scientifically verified answer. Metallurgist R. Balasubramania spent years studying the pillar's exact chemical composition, running tests that simply weren't possible until recent decades, and his research finally cracked the mystery. Ancient smiths had, almost certainly without fully understanding the underlying chemistry, worked a precise concentration of phosphorus into the iron during the forging process, likely a byproduct of the specific ore and smelting method they used, refined through generations of trial and error until it consistently produced this result. That phosphorus reacts slowly with moisture in the air to form an ultra-thin, almost invisible protective layer on the pillar's surface, called misawite. And here's the truly remarkable part. That protective layer doesn't wear away over time the way a normal coating would. It actually regenerates itself slowly and continuously as long as the phosphorus-rich iron underneath remains exposed to the air. This wasn't luck. This was applied materials engineering, executed with extraordinary precision more than 1,000 years before the phrase materials engineering existed anywhere in the world. Consider what that actually required in practice, without any of the tools we take for granted today. No chemical analysis, no way to measure phosphorus content in parts per thousand, no theory of oxidation or corrosion resistance written down anywhere. Just generations of smiths noticing, slowly and imperfectly, that iron smelted from certain ore sources using certain methods seemed to hold up better over time than iron smelted another way. That observation, repeated and refined across countless forging attempts over centuries, eventually produced a result so consistent and so effective that it has now outlasted the empire that made it by well over 1,000 years. The pillar itself carries an inscription, still partially legible today, believed to honor a ruler from the Gupta era, likely Chandragupta II. It was originally intended as a monument, a public statement of power and devotion, standing in what was then a thriving religious site. Nobody who commissioned it, and nobody who forged it, was thinking about metallurgy in the way we understand the word now. They were thinking about permanence, about building something that would outlast them. In a way nobody could have fully appreciated at the time, they succeeded in a far more literal sense than they probably intended. Modern engineers, when they finally studied it properly in the 20th century, walked away treating a religious monument as one of the most impressive corrosion resistance case studies in the history of metallurgy. And here's something that might genuinely surprise you. While Europe and much of the Middle East were pouring their iron and steel almost exclusively into swords, armor, and increasingly elaborate siege weapons, India largely pointed a huge share of its metal somewhere else entirely, into plows, into irrigation tools, into construction, into temple architecture, into agriculture that could feed enormous growing populations. Why would a civilization capable of forging legendary, history-defining blades choose to spend so much of its metal on farming tools instead of weapons of war? Maybe because a stronger harvest builds a civilization further? and for longer than a sharper sword ever could. Deeper plowing meant richer soil. Richer soil meant more reliable food security across good years and bad. And more food, generation after generation, meant India's population could grow and sustain itself in ways few ancient societies of that era ever matched. That's not a small foot. That's a fundamentally different philosophy about what a powerful material is actually for. Now step back and look at the entire arc of this story at once, from the very first fire to the pillar still standing in Delhi today. It starts with a shepherd's fire or a potter's kiln, accidentally freeing copper from ordinary-looking rock, a discovery hiding in plain sight inside technology people already had. That discovery leads to bronze, and bronze builds empires, entire civilizations constructed around one specific, scarce, imported metal that most of them couldn't produce entirely on their own soil. That supply chain, stretched thin across deserts and open oceans, is fragile by design, whether anyone realized it at the time or not, and it eventually breaks under its own weight, forcing humanity to finally look down at the one element that had been sitting quietly underfoot the entire time. And through every single stage of that journey, one civilization keeps reappearing, working largely on its own, pushing the material further than almost anyone else on Earth managed to, discovering iron independently centuries ahead of the empires that history usually credits first, refining that iron into a steel so advanced that one of history's greatest scientists, working with the best tools of his era, couldn't reverse engineer it, and forging a pillar that has defied rust, defied weather, defied time itself for 16 unbroken centuries, standing in a public square while empires rose and fell around it. None of this happened because anyone involved understood chemistry in the modern sense. Faraday didn't crack it. Even with formal scientific training, European science wouldn't fully explain any of it for another 100 years after his failed attempt. It happened because ordinary people, generation after generation, kept watching their fires a little too closely, kept asking what if this rock is different, kept refusing over and over again across thousands of years and thousands of miles to simply accept that a stone was just a stone, and that the way things had always been done was the way they always had to be done. Think about that the next time you pick up anything made of metal. The knife in your kitchen drawer, the frame of the car you rode in today, the steel beams hidden inside the walls around you right now, holding up the ceiling over your head without you ever thinking of it. Every gram of it traces back through an unbroken chain of accidental fires and stubborn human curiosity to a moment nobody planned and nobody fully understood, thousands of years before anyone on Earth had the vocabulary to explain what they were even doing. You are still holding the direct descendant of that very first accident. It's in your pocket, inside the device you're using to watch this right now. It's in the wiring running through the walls above your head. It's holding up the very building you're sitting in at this exact moment. It isn't a sharpened rock anymore. It's every fire someone refused to walk away from, every failed experiment someone tried again the next day, and every quiet, unglamorous act of curiosity that history mostly forgot to write down. That's the real story behind every piece of metal you'll touch today, and most people will never think about it once.